If you recall, yesterday we introduced the second part of the fundamental theorem of calculus, which is just the reverse of the idea of the first part of the fundamental theorem of calculus. So let's review. So let's suppose we have a continuous function on a closed interval and any value from that interval. The first part of the fundamental theorem of calculus says that the definite integral from a to b of f of x into x is capital F at b minus capital F at a, where capital F is an antiderivative of f. In the this first part of the fundamental theorem of calculus, we are using an antiderivative to calculate a definite integral. We want to find this continuous sum, and we can use the antiderivative to do it. This is how calculus deals with that weird part. Find this continuous sum that we're trying to find. The second part of the fundamental theorem of calculus says that capital F of x, defined to be the definite integral from c to x of f of t dt, is an antiderivative of f. What the second part of the fundamental theorem of calculus is doing is using the definite integral to construct an antiderivative. Really, what we're getting out of the second part of the fundamental theorem of calculus is that continuous functions have antiderivatives. We just might not be able to write a nice formula for them. We might not be able to add one to the exponent and divide by the new exponent. The second part of the fundamental theorem of calculus says that a continuous function definitely has an antiderivative, but you might have to build it yourself. The reason that this is significant is that a definite integral can be approximated to any degree of accuracy depending on the data that you have available. With area, definite integral is just length times width. We can always approximate that if we need to. But the idea is that we are using the definite integral to construct an antiderivative. That's what we're doing, and then that's the why of what we're doing. So now we've got this function, this graph that you may recognize. Yesterday, this was the graph of p of x. What I want to do today is look at a similar problem to the problem that we had yesterday, but phrased in a different fashion. So yesterday, I said let capital P of x be the antiderivative of p of x such that p of 0 was equal to -1. I want to reframe that with the second fundamental theorem of calculus. So instead of saying I really should use a different letter other than P because the capital and the lowercase kind of look the same. Oh well, what's done is done. Yesterday, when I set up the problem, I said let capital P be the antiderivative of p of x such that capital P of 0 is equal to -1. This is yesterday how I established that we are looking at the graph of the derivative p prime. So this is how we established yesterday, how we established that this is the graph of capital P prime of x. So this statement here is how yesterday I established capital P as the antiderivative, as an antiderivative. That is, we're looking at the graph. The graph that I have given you is the derivative of some function. This is how I established that yesterday. I also established the value, the particular capital P we want. I was able to say the antiderivative because I gave you a value of capital P. So I was able to say the antiderivative because I gave you this P of 0 is equal to -1. I gave you a value of P. So we also know the plus C part because we have have a value of P. So this is setting up the given graph as the derivative, the way that I did yesterday. Just say capital P is the antiderivative. Just saying that this is the derivative of capital P. Here's another way we can set up P, capital P, as the antiderivative. So I could also say, let capital P be the definite integral from 3 to x of P of t dt. Here I am doing the same thing using the second fundamental theorem of calculus. I am establishing that capital P is an antiderivative of little p. That is, I'm setting up P of x, little p of x, as the derivative of capital P. So this is just another way to set up capital P as the antiderivative of little p. So this is just another way to set up capital P as the antiderivative. Just another way to say that the given graph is the derivative of the function that we're interested in. Moreover, this includes a value of capital P. Moreover, this setup also includes a value of capital P. So this is making one specific antiderivative. Instead of a general antiderivative with the plus C, this will be one specific antiderivative. So here we have two different ways of setting up the same scenario. I gave you a graph, and I'm telling you that this is the graph of the derivative of some function. I make questions about the function whose graph this is the derivative of. This is the instruction here is read this as a derivative. Two ways to do that. Moreover, we're being specific. I'm being specific about which antiderivative I want. In this first setup, by telling you capital P of 0 is equal to -1. I just have to give you some value for the function. Capital P of A is equal to B. I just have to give you something about that function. Questions? Let's take a look at reading this derivative. So let's take a look at reading this derivative and then complete a table of values and then sketch a graph. And let's see if it will all fit in here. So here's what we want to notice. Let's suppose that p of x is the definite integral from 3 to x of p of t dt. I said that I have included some value. So first of all, this statement, using the second fundamental theorem of calculus, establishes capital P as an antiderivative of little p. It establishes little p as the derivative of capital P. It establishes little p as capital P prime. I also said that this includes a value of p. It's not as explicit as saying capital P of 0 is equal to -1, but we can evaluate based just on this setup. So because this second fundamental theorem of calculus business is new, this is how we evaluate the function. P of something is the definite integral from 3 to that thing of P of t dt. This is how we evaluate this function. So if I wanted to know for example, capital P of something easy, let's say capital P of 3, I want the integral from 3 to 3 of P of t dt. What's the integral, the definite integral from 3 to 3 of P of t dt always going to be? 0, because this question is saying it's going to be capital P at 3 minus capital P at 3, and that is definitely 0. The other thing we could say is how much is the function going to change on the interval from 3 to 3? It isn't. This is going to be a big problem when we start having teleportation, because we can have change in displacement in 0 time. But until that happens, you don't have to worry about it. That's why big calculus is trying to stop teleportation. Also, just recently, it was Pi Day. I don't even know if I even mentioned it. I don't celebrate Pi Day. I guess I'm math agnostic or something. I don't know. But Pi Day is a fake holiday invented by math companies to sell more math. I don't know about you, but there was like a professor that made that and put that on the screen. Some student took a picture of it and it became like, it like just started making the rounds. When you are a math teacher, you get that at least a dozen times on Pi Day. Everybody sends it to you because you're the math person in their life. You know what I mean? Like I know a lot of math people specifically because I'm a math teacher. My friend group knows a math teacher, knows a math person. So all math jokes come directly to me. This might be why I don't celebrate Pi Day, because everybody just celebrates it at me. And so I don't need to worry about it. I don't know. So here is one of the values that we get. I didn't explicitly state that capital P of 3 is equal to 0. I kind of implied that capital P of P is equal to 0. But now we have a value. We've got the value of P. And through the second fundamental theorem of calculus, we've set up capital P as an antiderivative. So this is how we evaluate this function. I picked starting at 3 because 3 was easy to evaluate. It's the definite integral from 3 to 3. That's going to be 0. If I wanted to calculate, let's say P of 4, If I want the definite integral from 3 to 4 of p of t dt, I want the area under the graph of p and above the interval from 3 to 4. So I want the area from 3 to 4. That's just a rectangle. The area there is 2. It's below the x-axis, so this is going to be a -2. This is the amount of change that we had from 3 to 4. But at 3, when x is equal to 3, we're at 0. We've decreased by 2, so now we're at -2. If I wanted p of 5, I'll find the integral from 3 to 5 of p of t dt. This is going to be the area of this trapezoid. There's -2 for the rectangle and a -1 for the triangle. So a total of -3. So this is going to be 2 for the rectangle. And 1 for the triangle. This 2 up here is just 2 for the rectangle. If I want to find p of 6, I have to look at how much the area from 3 all the way out to 6. So not only do I want to start at 3, and I want to end at 6. So I've got -2 for the rectangle, a -1 triangle, and then a +1 triangle. So there's a -2, this is a -1, and this is going to be a +1. These are the same calculations that we were making yesterday. We were looking at area under the curve and above the interval. Positive or negative. Positive for above, negative for below. When the derivative is positive, the function is increasing, area is positive. When the derivative is negative, the function is decreasing, area is reported as negative by the definite integral. In this case, the way we're evaluating it is the same as we were yesterday, and we're just thinking about it a little bit differently because it's set up with the second fundamental theorem of calculus. Any questions? So if we look at the integral, what's happening at P of 2, notice that the way that we've defined the function says start at 3, end at x. So if we want to evaluate P of 2, we integrate from 3 to 2. We don't just automatically integrate left to right. The function says start at 3, end at x. If x happens to happen before 3, that's the way you have to integrate. So notice that for P of 2, it's the integral from 3 to P of something is the integral from 3 to that thing of P of t dt. So if I said to evaluate at 2, we integrate from 3 to 2. If we want to read this as area, the area is going to come from the integral from 2 to 3. The integral from 3 to 2 is the opposite of the integral from 2 to 3. So the definite integral from 2 to 3, this is area below, which is a -1. But if we integrate, that's the integral from 3 to 2 will not be -1, it will be +1. So if we change the order that we're integrating, we change the sign of the definite integral. Capital F at A minus capital F at B is just -1 times capital F at B minus capital F at A. Change the order of integration in your definite integral, you change the sign. Any questions? Comments? Slide remark. This only seems like a lot to remember because it's a lot to remember, and you have to remember all of it, all the time, in perfect detail. Not all the time. Every time I'm in the room. So like this weekend, you will not have to, for the next after Friday, you won't have to think about definite integrals for like a whole week. Unless I show up where you work. You have to start thinking about definite integrals. Because I might bring a quiz with me. I'm just kidding. It'll be a whole ass test. That's like show up at your work. Maybe you're working at a checker at a grocery store, like all Now you grab a piece of paper and it doesn't scan. It's like, well, what the hell is this? And you look down at the piece of paper and it says Math 251 test. And then you're like, oh, what? And then you look up and it's me. I'm like, oh, you get 10 minutes, go. And there's like people in line. I'm like, well, what the hell? I'm like, well, they got to do a test. I just have to find out where y'all are working. And some of you are thinking, it's like, oh, ha, I got you there, Leach. I don't work. I'm out of work right now. Or maybe you just don't have to work. Then you're not technically out of work. You just don't work. In that case, I have to switch over to horror movie style. So you go into the bathroom late at night to brush your teeth. You open up the cabinet. There's a mirror right on the front because it's being shot from behind. So we see you in the mirror. You're like, oh, I got to get ready for bed. I'm going to brush my teeth. So you open up the cabinet and you get the toothbrush and the toothpaste. Then you close the cabinet. What happens? Murderer's right behind you, right? Then you turn around and they're not there. But this is the math version of that. You close the cabinet and the test is just stapled, not stapled, taped to the front of the cabinet. So you're like, oh, time for bed. Grab your toothbrush and the toothpaste. You close the cabinet, math test. So it's even harder because you have to do it in reverse because it's in the mirror. I can't do that one anymore because I've done it before and it's been overdone. So now like you'll be coming home one night, put a key in the door, the front door, and then all of a sudden an arrow just goes right into the door jamb. And you're like, what was that? Is someone shooting arrows at me? But there's a piece of paper tied to the arrow. So you're like, oh, what is this? Since you're in a horror movie, you don't just say like, oh, fuck this, I'm running inside. You have to stop and investigate the weird thing that's happening because it's a horror movie and the script says that you have to do the stupid thing. It's like, oh, where did this arrow come from? I'm going to do the perfectly natural human reaction and say, oh, look, there's a piece of paper tied to, and you unroll the piece of paper and it's a math test. And then from the bushes where I shot the arrow, I'm like, oh, you got 10 minutes. You know what I mean? Can you just picture it? These are the kinds of scenes that run through my head when I'm trying to do math. My therapist is like, oh, you shouldn't say that stuff out loud. I'm like, well, yeah, I know, but sometimes you got to stop talking about math. I'm just kidding. I don't have a therapist. I should, but I don't. As far as the reading goes, let's see. We have a 3, 2, a 1, 0, -1, -2, 3. So we had a couple of different ways of establishing that the given graph is a derivative of what you're interested in. You don't have to draw another one. It's the same one. As far as reading the changes goes, what we want to look at when we have a graph like this, the reason that I use line segments is that it's really easy to figure out what the areas are. So just take it a piece at a time. This first rectangle is, I'm going to label that a +2. Then the second rectangle, I'm going to label a +1. These are just the areas. And the sign is just whether it's above or below the x-axis. And then this third one here will be a -1. The area is -1, 2, 2. So changes below, area below is negative area, area above is positive area. And it's just a bunch of rectangles and triangles. Or if you're skipping steps, trapezoids. So this is how we would read what's going on. From 0, we increase by 2, then increase by 1, then decrease by 1, decrease by 2, decrease by 1, increase by 1. The other important thing to remember is that these areas represent changes, not values in the function. So from 0 to 1, we'll see an increase of 2. From 1 to 2, we'll see an increase of 1. From 2 to 3, a decrease of 1. From 3 to 4, a decrease of 2. From 4 to 5, a decrease of 1. And from 5 to 6, an increase of 1. These are just the changes that we see. We have to have some starting value. We have to establish a plus C. So if, for example, you're given a graph like this and some information that indicates that this is the derivative The areas are going to tell you the changes, and you're going to want to look for what the plus C is, something that establishes a starting value. So if I had said at the top, let capital P of X be the definite integral from 3 to X of P of T dt, this is me telling you that capital P of 3 is equal to 0. So if you're going to graph this or complete a table of values, that's where you're going to start. The changes come from the derivative. So 0 minus 2 is minus 2. Minus 2 minus 1 is minus 3. Minus 3 plus 1 is negative 2. Going backwards, 1 minus 1 is 0. 0 plus 1 is 1. Negative 2 plus 2 is 0. Now we have all the values that we want. Capital P of 0, capital P of 3 is 0. Then we decrease by 2 to negative 2. Then we decrease by 1, and then increase by 1. Before that, we had decreased by 1. Before that, we had increased by 1. Before that, we had increased by 2. This is the same shape that we had yesterday, but it has a different starting value. Notice that this one starts, P of 0 here is negative 2. Yesterday, P of 0 was negative 1. When we go to fill things in, notice that the derivative, so this is our graph of little p is also the graph of capital P prime. So when we go to draw the graph of capital P, we want to make sure we include the correct height, the correct location, so the correct starting value. We want to have the correct changes and the correct concavity. Those are the 3 things I'm looking for. There are 2 places where the derivative is flat, which means the function will have no concavity. So from 0 to 1 and from 3 to 4, those are places where the function is flat, so we see no concavity. From 1 to 3, we see that the derivative is decreasing, so the function is concave down. So we don't want to just connect these 2 with lines. We want to draw a concave down, flat at 2. And then from 4 to 6, we see the derivative is increasing, so we'll draw something concave up. Main thing we want to see is that when I say capital P of X is the definite integral from 3 to X of P of T dt, That is me establishing capital P as an antiderivative of the given graph. Questions? Comments? Snod remarks? How's everybody? There's only a couple days before spring break, so no one's going to have any questions right now. Everybody's like, oh, nah, I just need to make it to spring break. I can hear everybody secretly trying to cast silence on me. And I keep making the saving throw. And if you're thinking, there's no saving throw in silence, then I must be counterspelling you the whole time. Since you haven't seen me counterspell or heard me counterspell, it's specifically because I have subtle spell and enough meta magic to simply keep it up. All right, that's going to do it for today. I will see you all on tomorrow when we're going to practice a similar thing because I like spending way too much time on this. That's it for today. I'll see you all on tomorrow. Everybody have a good day and thanks for playing. Sign in on the sign-in sheet, and if you didn't pick up the work from yesterday, please pick up the work from yesterday.